Hi, this is Gordon Downs with Team 19063, Epileptic Sleep Seizure Detection and Notification System. More than 50 million people in the world have epilepsy, which results in seizures. An extremely unfortunate risk of seizures is sudden unexpected death in epilepsy, or SUDEP. The risk of SUDEP can be reduced if a patient receives care during a seizure. Unfortunately, products that you can buy now are inaccurate and expensive, so we designed a system that's both accurate and inexpensive.
Hey guys, I'm Alejandro Ortega, team lead for Team 19063. For our project, we propose a minimally invasive system that utilizes stereoscopic IR images and several post-processing techniques that reveal frequency components of our signal to better differentiate between regular motion and seizures during sleep, based on the occurrence of rhythmical contractions during tonic-clonic seizures. The end goal of this project is to feed that data into an AI model that will decide the probability that the motion corresponds to a seizure.
Our final system design is composed of three subsystems: the image capture, image analysis, and notification subsystems. These loosely correspond to our three most important pieces of hardware: an Intel RealSense D415 depth camera, a mini PC, and a caregiver's smartphone, respectively. I'll summarize each of the subsystems and their interactions here. First, the image capture subsystem collects data in the form of depth videos and sends that data to the image analysis subsystem. Second, the image analysis subsystem, which is running on the mini PC, receives those depth videos and uses them to determine whether a seizure is occurring. If a seizure is occurring, it sends an alert to the notification subsystem. Finally, the notification subsystem receives the alert and triggers an alarm on the smartphone of the patient's caregiver to alert the caregiver that their patient is having a seizure. Paraphrasing, our functional requirements were for the system to detect a seizure, notify the caregiver when the patient is having a seizure, provide information to medical providers in the form of logs of seizure occurrences, be open source, and be inexpensive.
One of the biggest obstacles for this project was to collect reliable data to train our AI model. We came across this amazing opportunity to create clinical trials in Bogota, Colombia, with the collaboration of two clinics. These clinics initially agreed to allow for the installation of a data collection system that would monitor epileptic patients overnight. The clinics also agreed to send reports of when seizures occurred for data tagging purposes once the clinical trials were approved. Given this, we focused our MVP not only to satisfy several system requirements for our main project, but also to be a data collection system that would enable us to gather reliable training data by detecting motion overnight, recording such motion, and then uploading the fragments to a cloud drive for later post-processing by the team. Thanks to the Agile methodology, we were able to focus the search iteration towards a data collection system by giving us flexibility on what we are building so that we can reach our end goals. Unfortunately, we had a couple issues along the way. First, we lost two team members, one during the first semester due to conflicts with the mentor, and the other during the second semester due to a conflict of interest between his employer and our project. Furthermore, because of the current pandemic situation, our clinical trials were canceled before they were approved. This forced us to rescope our project due to the loss of manpower and opportunities that were essential for us to complete our goals.
Since we haven't been able to collect training data at this point in time, our rescope as a result of COVID-19 is a system that does not detect seizures. Instead, we've refined our MVP, which collects depth videos of seizures, and made it more robust. We expect that this new, more robust data collection system will allow the open source community to finalize the development of the notification system, while we focus on maximizing our chances of collecting good training data, since the trials in Colombia are no longer an option, because good training data is the most critical part of an AI inferencing engine. Our new data collection system is focused on collecting a large amount of data and allowing users to tag the data as seizure or non-seizure activity without compromising on the performance of the final system nor the privacy of the users. With our BSD Plus patent, open source license, and ongoing support from our sponsors, we think this project has a really good chance of surviving and growing after senior design ends. Now I'll briefly go over some key verification results. So we wanted to capture images at a rate of at least 16 frames per second because that's a Nyquist rate for very fast seizure motion. So we got 30 frames per second, so we passed that test. We also wanted to analyze videos in real time, So that's at least 30 frames per second given our frame rate. We got 61 and 71 for our two image analysis algorithms, so we passed those tests. And then for motion detection, we set up 4 tests. We had beneath the bed sheet, no bed sheet, and we had motion and no motion. And in all 4 combinations, we got 10 out of 10. When motion was there, we detected it. When motion wasn't there, we said no motion detected. Although we never got depth videos of seizures to test it on, our preliminary results for our seizure detection algorithm were really exciting. Here on the left, we have a figure from the paper that we based our seizure detection algorithm. This top histogram is the average spectral density for seizure motion of an accelerometer strapped to a patient's wrist, which is like 1 point in space. The bottom histogram is the average spectral density for non-seizure motion with the same accelerometer setup. Our analysis suggested that when we expanded this 1 point in space of the accelerometer to many thousands of points with the depth camera, the same principles would hold. And when we tried with the demonstration, we confirmed this result. So here on the right are plots that we made using the depth camera. So you can see that the shapes are really similar. With no motion, you have a sharp rise towards 0 hertz. And then with the rhythmic motion, in this case seizure, in this case just waving a hand really fast, you can see the peak at the frequency at which the motion is occurring in both these plots. So this is really good evidence that our seizure detection algorithm was very much on the right track.
Hey guys, and welcome to our demonstration where we'll show you some of the functionalities of our system. But first of all, we'll show you the setup for our hardware. Our main component up there is our RealSense D415 IR camera, and our second component here is the computer. Now, we normally use a computer like this for portability and affordability, but for today's demonstration purposes, we'll use a laptop so you guys can see what's going on the screen. Now, the subject is going to go ahead and proceed to go to the bed and perform some non-seizure and seizure movements during sleep. You can see the subject starting to enter the bed. Now the subject is going to go ahead and perform some non-seizure movement during sleep. Now on the left, you can see the plots associated with the spectrum of that motion. Now the subject is going to go ahead and perform an imitation of what a seizure would look like. As you can see here on the left, we can see some high frequency components given because of the signal of the abrupt, rapid, and rhythmic motion.